Everyone, this is Sai Kumar Reddy. Today, I'm going to show demo of my thesis project, reinforcement learning based cost and latency optimization in Kubernetes enabled multi-cloud environments. And this project builds on custom RL scheduler that decides whether to place Kubernetes pods on AWS or Azure simulations to minimize cost and latency due to organizational restrictions on real EKS and AKS clusters. I used kind for a local simulation but integrated real world pricing from AWS and Azure documents. I will show the code structure, key files, Grafana monitoring, TensorBoard training, live results with 75% improvement and more. The full code is on GitHub as well. And yeah, first we need to activate our Kubernetes Conda, and then from here I have to run Kubernetes kind AWS. Yeah, and then here here in the multi-cloud foundation running kubectl config gets like contains showing both kind AWS ready to point out. Switching to kind AWS and kubectl get nodes, see the worker nodes with cloud AWS label simulating EKS. Same for kind Azure. Switching to run this YAML config sets different pods, subnets and ports for isolation. It also producible in minutes with no real cloud needed. I can show you in Docker. Yeah, here is my kind Azure worker, kind AWS and kind AWS worker, and these four are the many cubes of kind which are in Docker. And this is the project structure where RL scheduler environment has K8s multi-cloud env Python file. This is a gym environment where it loads real pricing CSVs and live prompters CPU, and also the values including AWS, cost of AWS, latency of Azure, reward is like negative weighted cost plus latency, where this runs with PPO with RLlib up to 80 iterations done. Yeah, where simple service YAML has Nginx file which can run the app. And here I am running the train and compare Python file of an RL scheduler, which it compares between the default scheduler and the RL scheduler, where I'm going to run this. Yeah, it's going to import the packages, and here the training is completed, and then now we are going to run this final evaluation. And yeah, now it's going to run. Cost of each episode for the 100 episodes for 20, 40, 60, 80, and the cost and the total decision total, and the agents, how many agents are choosing AWS and how many agents are choosing Azure. 43% are choosing AWS and 56% are choosing Azure. And improvement and the RL scheduler versus the baseline, and it's like approximately 75% is better it's showing. So yeah, And now let's run kind AWS cluster and kind Azure clusters to see the Grafana, to see the metrics in the Grafana. And from here we are going to run AWS kind to see the Grafana monitoring, and here we are going to run Azure Grafana to see the metrics. And yeah, and this is the TensorBoard dashboard where we can see the agent timestamps of total and episode reward mean, episode reward max, and the episode lean mean. And you can see all the dashboards over here, and the state buffer connection, view requirements, and rate tune, and everything dashboards we can see in TensorBoard. And coming to our files, where this train PPO file will trains the agent, and this is a final training file, and this file trains and compares the agent, and this is the evaluation file where if you run this we will get the output, like how many how like was the improvement better, how much is better is the improvement from the baseline to the RL scheduler by running the almost 100 episodes by using the locust. And yeah, here you can see the locust file where it will be loaded by the Nginx, where it is used to run the artificial batch jobs. And this is the configuration file for the kind AWS, and this is a configuration file for the kind Azure. And here we have real latencies and real prices files, and this is a normalized data, and these are the raw files where local AWS load exceptions and local AWS load files failures, and local AWS tags, local Azure failures, local Azure stats history, local Azure stats, and everything over here. And the data was saved in the data files, all this processed and raw data. Yeah, and we have seen all the TensorBoard dashboards for the episode reward mean scalar, which starts around -5 and which is improved steadily to -1.23 by 80 iterations. And it's a clear proof of PPO agent learned to balance cost and latency, and where the loss decreases smoothly. And now the most important part is results. By running the final evaluation.python file over 100 episodes, the average cost is like $1.234 with reward function of -1.23, and the agent placed like the pods on Azure with the 56% almost, and AWS of the time because of the lower more cost, and only 43% on AWS when it needed load balancing compared to the default scheduler baseline of $4.76. That's the 75% of reaction cost. Latency also dropped from like 75 milliseconds to 70 milliseconds. And in conclusion, this project has successfully built and evaluated a reinforcement learning scheduler that significantly outperforms the default Kubernetes scheduler in a multi-cloud content, even when limited to local simulation. The key insight is that meaningful optimization is possible using only publicly available vendor pricing and latency data, where the complete code, checkpoints, screenshots, and report on GitHub are the which are ready for the production or to extend on the real clouds in future. And thank you for watching my video. Thank you.